Hello, everybody. Welcome back. I obviously do not have your exams back yet, but I'm almost done with the old take-home exam, so this will be coming back shortly, and I hope to get your actual exams back by the end of this week. At the very, very latest, it would be next Monday, but I'm aiming for Friday or even Wednesday of this week. But you know, when I aim, I miss. So that's the plan. So it was a hard exam, and I think there's going to be a curve. Although you're doing really well, the little I've looked at. So I'm not saying there needs to be a curve because you're doing so horribly or anything, but I think it was maybe a little too hard for what it was. Not too hard if it was a homework or something like that. So don't be too stressed about it. Let's see how it pans out. So welcome back. And we are still talking about continuous time Markov chains and specifically birth and death processes. And we are just getting into stationary distributions. So last time we looked at, am I actually talking in this mic now? Yeah, last time we looked at Kolmogorov's forward equation, and we were using that to try to derive an expression for the stationary distribution for a birth and death process. So we were talking kind of about a generic birth and death process, and it has rates, transition rates. So rates of transition, and we have names for those. We call them Qi, I plus 1 to be the rate, the instantaneous rate of change from state I to state I plus 1. And that's our birth rate when the current population size is I. And we have a Qi, I minus 1, which is supposed to be the death rate when the current population size is I. So that's our mu I. We have a sort of rate of staying in place, if you will, and that is the negative of the sum of the other things. And then we have that all the other rates are 0 otherwise. And so we can put those in a matrix, and we call it the generator matrix. And with the generator matrix, we get Kolmogorov's forward and backward equation. So we were using last time, seems like forever ago, Kolmogorov's forward equation, which is the one that says that P prime of T, so that's the derivative, the element-wise derivative of the matrix full of transition probabilities of starting at I and ending in state J at T units of time later. We had that this was P of T times Q. And in particular, if you just want to look at like the ijth entry, then a Pij of T, the derivative of that, is the sum over K of Pik of T Q Kj. And so using these Qs up here, you know, there's only 3 of them that are non-zero. Last time we wrote out a couple of equations. So plugging these guys in, last time we wrote out the Pi0 prime equation. And this one is negative lambda 0 Pi0 of T plus mu 1 Pi1 of T. And then we wrote out the rest. So in general, the Pij prime of T, and the reason these are separated is because that first equation is the only one where you have only 2 terms. In the other equations, you have 3 terms. So we had lambda j minus 1 Pi j minus 1 minus lambda j plus mu j Pij of T plus mu j plus 1 Pij plus 1 of T, and this holds for j greater than or equal to 1. So here's just about where we were. We were taking limits of these equations. And I did just state as a non-proven fact and gave you a reference last time, because it's kind of beyond our, some things are beyond our scope, like we just don't have time to talk about things, but some things are beyond our reach, maybe. This would be a lot easier if you had some measure theory. Whatever it is, it's a big detour. So we showed that for a birth and death process if the rates are kind of nice, meaning you know what, it doesn't matter if they're nice. I was going to say if the rates are kind of nice, then the limiting distribution exists. And we know that a limiting distribution is stationary. But if we have like a birth rate that's way higher than our death rate, we're not going to get a stationary distribution, but we're sort of going to get a limit that's going to put all probability 1 on infinity if what we're actually looking at in our chain is the number of people in the system in the limit. So if the birth rate is really high compared to the death rate, then we're not going to reach an equilibrium. We're just going to blow up the population. So assume that the limits of these probabilities exist. And if they do, then the limits of the derivatives are going to 0 because these limits are going to, well, that should have an of t, because these limits are going to constants. And therefore, the derivative limit should be going to 0. And so we took limits and we said now that our two equations turn into 0 is negative lambda 0. And then this is going to be pi 0. So that I'm not going to circle every one of these, but this came from this, right? And that says no matter where you start, so the I doesn't matter. If you let t run off to infinity, you will be in state 0 with this probability we're calling pi 0. And then to finish this out, we have plus a mu1. And then over here, I'm going to let t go to infinity, and the I is irrelevant. And we are going to pi 1, like the long run probability of ending up in state 1. And then for the second equation, I've got 0 is lambda j minus 1. This is going to be pi j minus 1, which comes from this guy, minus lambda j plus mu j pi j plus mu j plus 1 pi j plus 1 for j greater than or equal to 1. And these are the two equations we're using to solve for our stationary distribution. And so I can use the first equation here to figure out that pi 1, the probability of us finding one individual in this population at some point in equilibrium is lambda 0 over mu 1 times pi 0. What's pi 0? I don't know yet, but I'm going to write out an expression for pi 2 in terms of pi 0 and pi 3 in terms of pi 0. And then we can figure out what pi 0 is by making sure our probabilities add up to 1. So let's look at this guy with j equals 1. I get 0 equals lambda 0 pi 0 minus lambda 0, lambda 1 plus mu 1 pi 1 plus mu 2 pi 2. And so I'm trying to solve for pi 2. And I do know that pi 1 was lambda 0 over mu 1 pi 0. So if you plug that in, i.e. multiply by this coefficient and move things around, you will get to pi 2 is lambda 0, lambda 1 over mu 1, mu 2 pi 0. And if you do one more, and then I would go to an inductive step, but maybe one more to see a pattern. So if you write out the second of these two equations up here with j equals 2, you now know pi 1 in terms of pi 0, and now pi 2 in terms of pi 0. So you can plug those in and get pi 3 in terms of pi 0. And you get pi 3 is lambda 0, lambda 1 up to lambda n minus, sorry, I'm generalizing, lambda 2 over mu 1, mu 2, mu 3, pi 0. You know you did something wrong if you end up with a mu 0 in the denominator, because that's the rate of people leaving the population when there's currently 0 in the population. So that's always 0. So if you're trying to remember, like, one of these starts with the 0 index and one starts with 1, definitely you want the mu's starting with the index of 1. So if you maybe want to like postulate here that in general pi n is lambda 0, lambda 1 up through lambda n minus 1 over mu1, mu2, up through mu(n) times pi 0. And I was planning on proving it. It's really rather boring. It is a proof by induction. So you take that second equation up there that had the 3 terms, and you assume you already know 2 of them because there was like a pi j minus 1 term and a pi j term and a pi j plus 1 term. So what is induction? You assume you know something up to a certain point and you try to show it at the time plus 1 point, right? So if you're trying to find pi j plus 1 and you know what these are, then you plug these in and it's all equal to 0. And you can solve for this and see that it has the same form. So we can prove this by induction, and I am happy to do so if anyone requests that on N. So let me know. All right. Okay, so let's, I did say that everything's in terms of pi 0. So here's what we have right now. We've got a birth and death process with birth and death rates, lambda I, mu I, and obviously the lambdas are the birth rates and the mu's are the death rates, and the I is the current population size. And the stationary distribution for the number of people in the population. So if you let x of t be the number of people, individuals, cells, particles, balls, socks, urns, I don't know, people in the population at time t, then we know that the stationary distribution now is pi n. I just wrote it, but I'm kind of summing this up. We're going to use this so much. So I'll put it in a nice box. Mu n pi 0. And I do want to add to it and say where pi 0 is what you need to make these pi's add up to 1. So where pi 0 is what it needs to be so that the sum of all the pi's, including pi 0, is 1. And we're about to do an example. So if that doesn't make sense, it should in a moment. So our first example is our first formal queue or like a lineup process. So we're getting into the queuing portion of Markov chains, and we've seen one queue already, although we didn't have the language of queuing theory yet. And so I'm just going to do this one by example and describe it in the example. So we're going to talk about something known as an MM1 queue. And let me describe it first, and then I'll go back and tell you what the M's represent and what the 1 represents. So we've got a single server. We have people, customers, widgets, information packets. I'm just going to say customers. Customers arriving according to a Poisson process with rate lambda, which means, among other things, that the times between arrivals are exponential with rate lambda. And the service times, the time it's going to take for the cashier to serve people, those service times are assumed to be IID exponential with rate mu. And I know I want to go back to talk about what the M and the 1 mean, but this is usually visualized by a box like this being the server, and then you have an input process, and then a service time, and then they leave. And so the first M, actually both M's in the MM1Q stand for memoryless. The lack of memory property. This tells you that you've got exponential stuff going on. And the first M, the one that I've circled, is telling you that the times between the arrivals are exponential with some rate. And the second M tells you that the service times are exponential with some rate. And the third thing is the number of servers. So the first letter is something about the distribution of arrival times, the inter-arrival times. The second, the distribution of service times. And the third one, the number of servers. We're going to talk about an MMK queue where we have K servers. And we're going to talk about a GMK queue where G stands for general, and it's everything that's basically not exponential. So that's where it gets its name. And I don't know how to draw this. Do you draw this like this, where there's people and really strange looking people, and this person's in service, or do you actually pop someone in here and say these people are in the line? I don't know. People do it both ways. Well, they don't draw people, but they usually draw like little circles representing customers. So you can either draw it like that, or you can take this one out, but then that means that the first one is actually in service. All right, so this is our first queuing model, and I want to know two things. I want to know a lot of things, but right now I want to know two things. One is the stationary distribution of the number of customers in this queue in equilibrium. And along the way, I want to come up, well, hopefully I won't have any, but maybe we're going to see, yeah, okay, sorry, I didn't have my chat open. Yes, we are getting to the part where I try to explain why it's better to not switch lines at target. And the question, what do the two M's mean again? They mean memoryless, which means we're talking about exponential distributions for our inter-arrival times and our service times. Lack of memory. I don't know, I prefer to call them, no one calls them an LL1, but lack of memory sounds better to me. So we're going to find the stationary distribution, and along the way, maybe find some restrictions on lambda and mu. For example, I want to know in the long run, once this thing reaches an equilibrium, the probability that I see n customers in the system. And that is an important distinction from in the queue. And some people saying in the queue mean in the system, but then some people say, isn't the queue the people out here? So we've got people in the system, like in my picture, a total of 2, or we have people waiting in line, waiting, and there's 1 in my picture. And we have to be careful about what we're, a lot of people will say there's 2 people in the queue, meaning the queuing system, but that doesn't mean there's 2 people in the actual literal queue, which is a line. So I'm going to be really careful and always say in the system, or the ones waiting for but not undergoing service. Okay, so if they're coming in at a really fast rate compared to the service rate, this thing's going to blow up. And I don't think we'll find a stationary distribution. I think we'll find a line that's getting longer and longer and longer. And let's see what happens. So this, the MM1 queue, is a birth and death process with constant birth and death rates. So we've got our birth rate when the population size, you know what? I just said all of this stuff about how important it was to be really specific about what you're talking about. So I'm going to let X of T be the number of customers in the system. So this is in line and in service. Comes out cleaner this way. And then we can always translate back to what we want if what we want is only the people standing in waiting. So the number of customers in the system. And so that's in service and those that are waiting. And so now with this X of T, we have a birth and death process with constant birth and death rates. This is a birth and death process with birth and death rates. So lambda sub I is supposed to be the rate of increase of birth in the population when there's currently I in the population. And this is a constant lambda. This could easily be adjusted to be something else if you have the idea that customers are going to go away if the line is too long. So when I gets too large, maybe the rate of arrival is slower. But that's not what we're dealing with yet. This is the most basic queuing model. And our death rate is always a constant mu for I greater than or equal to 1. And this one is for I greater than or equal to 0. So as long as someone's in the system, the time to the next departure is exponential with rate mu. And we always have mu of 0 is 0. So let's go to our new favorite formula for a stationary distribution. That's what we want to find here, a stationary distribution. This is lambda 0, lambda 1, up through lambda n minus 1 over mu 1, mu 2, up through mu n, pi 0. And all of my lambdas are just lambda, and all of my mu's are mu. And I don't have a mu 0 in here, so I don't have to worry about that one special mu. So I've got n of them on the top and the bottom. So I've got lambda over mu to the n pi 0. And to finally figure out what this probability is, I need to figure out what pi 0 is. And this is where you want to add up all the probabilities and set them equal to 1. So let's find pi 0. So I'm going to need 1 to be the sum as n goes from 0 to infinity of the pi n's. And a lot of times when you use this approach to getting a stationary distribution for birth and death processes, the formula that you write here may not hold when n equals 0. This one does, because if I plug in n equals 0, I get pi 0, and this goes away. So I get pi 0 equals pi 0. So this formula actually holds even when n is 0. That's one thing you have to be careful about in the future. So this is for all n greater than or equal to 0. And therefore, I get to plug it in over here. This is lambda over mu to the n pi 0. Now, if the recursive thing you have does not hold when n is 0, then you would instead just say, okay, this is pi 0 plus the sum from 1 to infinity of the formula I found. It's just that the formula still holds when n is 0 here. And if you pull the constant pi 0 out, we have a geometric sum. And you know what that sums to as long as the thing is in magnitude less than 1. And if it's not, it blows up. So this is a nice geometric sum, and it will sum up to 1 over 1 minus lambda over mu if lambda over mu is less than 1. You're probably used to saying if the absolute value is, but these are exponential rates and these are forced to be non-negative. So usually we don't even bother to say that in Markov. I.e., lambda less than mu, which makes sense. That's the rate of people coming in versus the rate of service. And if they're coming in faster, in this case, they're coming in at a slower rate, but if they're coming in faster than the service rate, it's going to blow up. But if not, then we get, let's see, from this, I've got that pi 0 is 1 minus lambda over mu. And then from our relationship above, I've got pi n is, it is 1 minus lambda over mu to the n. Which actually, so this is for n greater than or equal to 1, but it actually also holds in the 0 case. It's just that some of these problems, you won't get the formula to be consistent in the 0 case. By blow up, I mean that, so I'm trying to say in the long run equilibrium, if you just approach the queue and you see 18 people in the system, what is the probability you'll see those people once it's in equilibrium? If the rate parameters are not nice like this, our equilibrium distributions are identical to our limiting distributions because we sort of restricted ourselves to a little bit of an easier world. If lambda is greater than or equal to mu, this line is going to blow up. They're just not being served fast enough. So blow up meaning the number of customers is going to shoot off to infinity, and we really can't talk about a distribution. You recognize this, right? It's the geometric. This is a geometric distribution. It is the one, well, it starts from 0 because it allows for 0 people. So this is the geometric distribution starting from 0. There's one that starts from 0 and one from 1, with the p parameter for the geometric. So remember, that's usually written like 1 minus p to the n or x. I guess I'm usually using an x times p. P here is 1 minus lambda over mu. And so I can tell you right now, without any extra work, because we know some things about the geometric, we can talk about the expected number of customers in the system in equilibrium. It's the expected value of this geometric. And I will in a moment. But before I do that, well, let's do it. Yeah, this is a good time to do it. Expected number of customers in the system in equilibrium. In the homework that's going to come out this week, I may forget to say in equilibrium, and you can assume that, because if not, I would have had to tell you exactly what I meant. I would have had to say the store opened at 9 a.m. and I want the expected number of customers there at 10 a.m. You know, I would have had to give you some really specific thing to find if I didn't say in equilibrium. So this is, yeah, the one starting from 0. I always have to stop and think if this is the 1 over p or the 1 minus p over p. This is the 1 over p. This is 1 over p, which in our case is 1 over, let me add this stuff up. So mu minus lambda over mu. So it's mu over mu minus lambda. There's the expected number of customers in the system, so including the person being served, when the queue is in equilibrium. And the denominator makes sense, right? Because we know that we need lambda to be less than mu. So it's not like we're getting a negative expected number of customers or anything weird like that. Because we saw a geometric thing and I was trying to give you the parameter p. But here's notation that's used in all different sorts of queuing scenarios, multiple servers, weird routing behavior. This is a rho, not a p, the Greek letter rho. And it's different for each queuing system. But in our case, it's going to be the lambda over mu, and it's known as the traffic intensity. And this queue is stable if this is less than 1. Otherwise, it's unstable. So this is 1 minus p over p. That was wrong. And that will give you, should give you lambda over mu minus lambda. So that's just wrong. Thank you for catching that. 1 minus p over p, which is lambda over mu over 1 minus lambda over mu. And if you multiply the top and bottom by mu, you'll get lambda over mu minus lambda. So this thing called rho is a traffic intensity, and we need rho less than 1 for, and this is a rho, not a p. I know they look really, really similar here. We need rho to be less than 1 for stability. Stability meaning it's not going to blow up. Okay, what else can we solve right now about this queue? I have a couple of questions for you. So we've got an MM1 queue. We've got the input rates lambda and the service rates mu, which are always the letters used by default. The question is, what is the problem that a person who shows up to the system in equilibrium will have to wait? So probability, a person showing up at, not really using the word random very well, technically, a random time when the queue is in equilibrium. And what do I mean by equilibrium? You open the store and there's no one there. And so you didn't open it stationary. You didn't open it with a geometric number of people there. It has to go for a while until it defaults into this geometric mode. What is the probability a person approaching will not have to wait? Oh, yeah, I was writing in equilibrium, which, as I was saying before, you can assume, because otherwise I would have had to say specifically, the store has only been open for 30 minutes and we started with 0 people, and I don't know if it's in equilibrium yet. What is the probability? We have this number of people at time t, and that's a Kolmogorov equation thing. What is the probability a person showing up at a random time when the queue is in equilibrium will have to wait? So the answer here is they won't have to wait only if the queue is empty. So this is going to be 1 minus the probability they won't have to wait, which is the probability in equilibrium that the queue is empty. So this is 1 minus lambda over mu, or lambda over mu. We have been doing things like this for a while, and it is high time this week, not today, that I justify this, because I've been squishing some things by you. This is not just an arbitrary time point. This is a pretty specific kind of time point. It's when the person shows up, what they see ahead of them. Do they see? So the queue is in equilibrium and a person shows up. What do they see ahead of them? Do they see stationarity? Let me give you an example where someone would not see stationarity. If a departing customer looks at the entire system at the instant before they leave, then there's always one person in the system, at least, them. So we never got down to the 0. It doesn't follow the same distribution. But we're going to prove this week something called the pasta property, and it stands for Poisson arrivals C time averages. And it says that if the external process of input to even a complicated queuing network follows a Poisson distribution, the arrivals see stationarity or time averaging stuff ahead of them. We're also going to see that the departure people see stationarity if they look behind them as they leave. I like to call that antipasta, but it's not true. That word is already, or that acronym or whatever it is already used for the opposite of a pasta chain, which is if arriving people see stationarity, are the inter-arrivals necessarily Poisson? We're not going to be going there, but I just like talking about pasta and antipasta. We're going to talk about pasta. What else can we talk about here? I'm going to ask another question about the MM1. So in equilibrium, what is the expected number of customers waiting in line? Now, this is different than the number in the system. And your first instinct might be to subtract 1, but that's not quite it. So what is the expected number of customers waiting in line? Waiting for service. So not the one being served. Waiting in line, waiting for service. So this does not include the person in service. So as I was saying, your instinct might be to just take our old expectation, which was lambda over mu minus lambda, and subtract 1. But the problem with that is you only subtract 1 if there was, so you've got the person in service, and you've got these people in line, and you're trying to figure out the expected number of people over here. And we've just derived an expression for the expected number of people here. So you want to subtract 1, but you don't want to subtract 1 if there's no one in the system, or there's exactly one person in the system. So exactly one person in the system means the picture looks like this. And so there are 0 customers waiting in line. So the answer is going to be, we're going to have 0 if there's no one in line, if there's no one in the entire system, I mean. So with probability pi 0, there's no one in the entire system, so there's certainly no one in line. We're also going to have 0 if there's only one person in the system, because that person is in service and not in line. If there's 2 people in the system, that's when we start having people waiting in line. So we get one person waiting in line with probability pi 2, where there's 2 people in the system. and 2 people in line with probability pi 3 when there's 3 in the system, etc. And this is the sum as n goes from 2 to infinity of n minus 1 pi n. And we have an expression for pi n. I'm going to plug it in. And I could pull out this guy because it's constant, but I think it's going to be easier to leave it in and manipulate this to look like something we know about the geometric distribution. So the first thing is, I don't like that sum starting at 2. That's just weird. Should we make it start at 0? That would be weird because this would be negative. Let's go down to 1. So I'm going to re-index this so that n starts from 1 and goes up to infinity. And so if you look at the previous expression, the first, this first guy here takes on the value 1 when n is 2 and 2 when n is 3. And so now I'm replacing this with just an n, like if I re-index that way. And then the 1 minus lambda over mu is still the same. And I want this to take on the value 2 for my first term. So that's going to be lambda over mu to the n plus 1 if I re-index starting from n equals 1. So if I were to take out the extraneous stuff here, this n and this sum, this is the expected value of a geometric that I'm sure to screw up again. So let's take out a couple of lambda over mu's. I'm going to take out lambda over mu squared. And then I've got the expected value of capital N, where capital N is the geometric, the one that starts from 1 with parameter p equals 1 minus lambda over mu. And that is the one. Before I had the geometric starting at 0. Now the geometric starting at 1 has mean 1 over p. So this is going to be 1 over p, and this is p. So the answer here is lambda over mu squared 1 over p, which is 1 minus lambda over mu. And if you multiply like the top and bottom by mu, then you have lambda squared over mu over mu minus lambda. So we have lambda squared over mu minus lambda. Or another way to write this would be lambda over mu times lambda over mu minus lambda. And this is the expected value of the number of people in the system, period. And this is the probability that there is going to be at least one person in the system, because this is 1 minus pi 0. So we could have approached this whole question, what is the expected number of people waiting in line, with conditioning on whether or not there was someone in the system. Again, this is the expected number of people in the system, and this is the probability there's at least one person. This is kind of fun, right? This is kind of refreshing and simple once we derived that formula in a box that we're going to make a lot of use of. So the whole pi n is the product of the lambdas over the product of the mu's times pi 0. We're going to use that a lot. Okay. What is, for the MM1Q, the expected waiting time for an average customer in equilibrium? So let's find this. This is a little bit tricky. I'm going to let W be the waiting time for a typical customer when the system is in equilibrium. And this random variable W is actually neither continuous nor discrete. It's a mixed random variable because we can take on the value 0. So we've got part of the answer here. The probability that W is 0, the probability that someone who approaches has no wait, is the probability that there's no one in the queue. That's the only way you have no wait. You walk up and no one's in service, no one's in line. And this is 1 minus lambda over mu. So you can't have equal to probabilities for continuous random variables. But this is kind of mixed. There's one point where we can actually land with positive probability. And now we're going to find the PDF for the W in the case where it's greater than 0. Let's do it. If the customer arrives when there are n people in the system, that's including the one in service, then that person has to wait through n-1 service times and the remainder of that one person who was already in service. But by lack of memory, that remainder service time is still exponential. So this person has to wait through n exponential rate mu service times. So he or she has to wait for n exponential rate mu service times. And I just want to emphasize that it's actually n-1 plus the expected remaining time of the person in service. But by lack of memory, we interrupted that service, and how much time do they have left? Still exponential with rate mu. So the expected remaining time for the person in service. And this is still exponential with rate mu. That's how long it takes to get served. Then this is by lack of memory. So if the customer arrives when there's n people in the system, they have to wait for a gamma amount of time. So the waiting time. So we're sort of in a kind of conditional setting here. If the waiting time is going to be greater than 0, then the waiting time is gamma with parameters n and mu, because it's the sum of n exponential service times. So I am out of time, but next time I'm going to pick up here and we're going to go for the PDF in this conditional case, and we're going to condition on the number of customers in the queue and use the gamma distribution and our new geometric distribution to figure this out. Next time on Markov chains.